করবে সেটা
Good morning, everybody.
Good morning, sir.
Hello, can you hear me?
Yes, sir.
Okay, fine. Okay, so let us begin. So, have you got any information from the university that whether your classes will begin from 16th November or not? Have you received any information?
Sir, we haven't been informed from the university yet.
Yeah, okay, let us see what happens. So, I think in the last class we had stopped at this point, right? That is, we calculated the power received in any radio link, and associated with that we have also done, I think, one or two problems, right? These two problems we have done, right? This one of a satellite at a distance of 40,000 kilometers or so. Okay, now actually, one thing that I want to discuss with you is that in the new code structure that we have for BTech, there it is explicitly not mentioned that whether there is any course on satellite navigation or not. This particular course on satellite is on satellite communication. But earlier, in the navigational electronics, there was a component on satellite-based navigation, because satellite-based navigation, we are using it so frequently nowadays. Okay, we are using it simply on our phones, like on Google Maps, and then also on these app cabs. So it is very much required nowadays that at least uh, BTech students should have at least the basic idea of how satellite navigation works. You may not go into the details of it, but at least you should know that. So, towards the end of our course, if time permits, maybe I will also discuss a few things about satellite navigation. Okay, because I don't think there is any opportunity for you to learn about it in the subsequent semesters. I'm not sure if there is anything on navigation electronics nowadays in the present course in the sixth, seventh, or eighth semester. So that way, what I'm planning is that after we finish whatever we had to discuss on satellite communication, maybe we will spend a little bit of time on satellite navigation as well. So moving ahead with the calculation of how to set up a radio link and how to quantify that the quality of that particular radio link, because simply saying that a link is good or bad, that is subjective. It uh, it imparts different information to different people. Okay, so that is why it is always necessary to quantify that particular thing in terms of both the power received as well as from the perspective of the earth station, that means the receiver which is receiving the signal on the surface of the earth, in terms of a parameter which is known as the G by T ratio. So let us discuss this. So by now, from your analog communication classes, I think you are familiar with the concept of noise temperature, okay, in the receivers. And that noise temperature is contributed by the different subsystems or blocks in a communication receiver. And this noise temperature actually, this is a way of understanding how much thermal noise is generated by the active and the passive components in the receiving system. So before going into the mathematical part of that, if you kindly recast your mind, recall that different block diagrams of a super heterodyne receiver. I think you are already very much familiar with a super heterodyne receiver, right?
Yes, sir.
Okay. So there, actually, if you just recall the different steps, the different blocks. So starting from the antenna, we have first an RF amplifier, then a mixer with a local oscillator, that is followed by an IF amplifier. Then comes the detector, which is very often like a square law detector. And thereafter, you go on to the low pass filter integrator stage, and finally to some output amplifier before you are sending that output to some kind of a display or some kind of a final recording stage. Okay, so these are in a nutshell the basic block diagrams of a super heterodyne receiver or a communication receiver. So ideally, the initial stages of a super heterodyne receiver will have large bandwidth. And as you progress down the different blocks of the receiver, that means starting from RF amplifier, then on to the mixer, local oscillator, then the IF amplifier, detector, and so on, the bandwidth is gradually tapered off so that the undesired signal components or out of band signals, they are gradually removed from the signal. So what we can understand is that this bandwidth is made large at the initial stages because in case of communication receivers, I mean particularly receivers which are receiving signals from satellites, or also in case of radio astronomy receivers, they are receiving signals from radio stars which are way beyond our solar system. So the signal level is extremely small, very low, like 10 to the power minus 18 watt or something like that, typically for radio astronomy receivers, and about 10 to the power minus 12 watt for satellite receivers, the received signal. So that is why the idea is that at the initial stages, we keep the bandwidth as large as possible so that whatever signal along with a large amount of noise is coming, we will accept that. And then, depending on the tuning frequency, we will select the bandwidth around that center frequency and gradually remove the out of band noise components. And if you are familiar with the representation of this kind of a receiver by two-port devices, like a device having an input port and an output port, that's simply a two-port device. So if you represent the different blocks of a communication receiver with this two-port concept, then each of these individual two-port is contributing some amount of noise temperature to the overall system noise temperature. And the relationship which we find normally, let me see if I can write it over here somewhere. So if I say Ts as the system noise temperature, that will be like T1, that means the noise temperature from the first stage, plus the noise temperature from the second stage divided by the gain of the first stage, then the noise temperature from the third stage divided by the product of the gain from the first two stages, and that continues. So what we can understand from this is that in case of a typical communication receiver, which may be of a super heterodyne type, because the gains of the individual stages are very high, because we are dealing with a very weak signal. So under that kind of a situation, as we go to the higher order terms, the denominators become extremely big, because we are having the product of two large values. The gains are very large for the initial stages, so as to boost up the signal. And so the higher order terms, they gradually become insignificant. So it may be the first two stages, or at best the third stage at best. But beyond that, the contribution of the noise temperatures from the other stages, they become insignificant. So that is why it is said that in case of a communication receiver, when you are representing the different blocks of the receiver using two-port devices, only the first few stages, maybe the first, second, and sometimes the third, not always, sometimes the third stage, they contribute the noise temperatures to the system. The remaining parts or the subsequent sections or blocks, they do not contribute anything, because they become too little or too insignificant. So that is why to a radio engineer, it makes sense to design the first few stages of the amplifier with keeping in mind that the noise contributions from them should be as low as possible. That means T1, T2, T3, they should be as small as possible, and G1, G2, they should be, or G3, they may be as large as possible. So that also agrees with our overall physical understanding, because if I'm trying to tune or trying to receive a very weak signal, the ambient noise is much larger than the signal component, and while trying to receive that, if I'm using a receiver where the individual blocks are contributing large amount of noise, then that makes my task even more difficult. So that is why we should try to see that the overall system noise temperature should be as low as possible, and that could be ensured only when the first few stages, they contribute very little noise but have very large gains. Okay, so that way, in case of a satellite receiver, satellite signal receiver, or any other kind of communication receiver, the first few stages, they assume importance when we are trying to calculate the overall system noise temperature. And another very important thing to remember is that suppose in the detection stage, if we are using a square law detector, then you have to remember that the output of that is equal to the input voltage amplitude squared, right? The output power is proportional, I should say, to the input voltage amplitude squared. Is it correct for a square law detector?
Yes.
So herein you can understand that the linearity of the signal is lost. That means in all the previous stages, starting from the RF amplifier, then the mixer, local oscillator, and the IF amplifier, basically the output signal was proportional to the input with some proportionality constant or things like that. But once the signal passes the square law detector, it is no longer a linear variation of the output with respect to the input. Rather, the output becomes square of the input voltage amplitude. So in a super heterodyne receiver, we could also, distinguish the entire receiver into two blocks, two broad subsections. One is the linear one, where the signal maintains a linearity with respect to the input and the output, and the latter half of the receiver where the signal does not maintain a linear relation between the output and the input. And also, there is a high frequency as well as a low frequency part of the receiver. The initial receiving stage up to the IF amplifier stage is the high frequency part of the receiver that having read about super heterodyne receiver, and subsequent portion that is the low frequency part of the receiver. So that way, these are small things which are which you should have learned in your communication classes, but they are equally applicable for satellite communication, because as you can see that as soon as the linearity of the signal is disrupted by passing the signal through a square law detector, there are additional frequency components, okay, like for example, the square of a frequency. So if it was like something cos omega t, it becomes cos square omega t. So cos square omega t means that you can resolve it into cos of 2 omega t term. So that means a higher frequency is generated when the signal passes through that kind of a nonlinear device in the receiver. Then, because at microwave frequencies, you see, we know this basic physical concept that a black body having a physical temperature of about T Kelvin, it generates electrical noise over a wide bandwidth, and that noise power is given by this expression, the product of Boltzmann's constant, this capital T, and the bandwidth. Okay. So this T is actually, the noise temperature of the associated device. And this parameter, the product of K into T, this is the noise power spectral density. I think you have heard about Boltzmann's constant, right?
Yes.
Okay. So this product of K into T, you can see this is invariant with frequency. I mean, for a particular device, it is a constant for all radio frequencies up to very high values of frequency, like maybe 300 gigahertz or so. So in the last class, I think we had derived the expression for this received power. Okay, either in terms of this relation, the relation in terms of decibel, or the relation in terms of this linear part, the linear relation. So what we can say is that then the carrier to noise ratio, in place of the carrier, you put the value of the received signal, that is given by Pt into GR divided by this KTB, okay, Pt into GT, sorry, this will be GT, by KT into B, okay, by GR. So that is the component of the transmitter power. That means this power was transmitted, and this KT into B is the corresponding noise power. So what we get is basically this GR and GR in the numerator and the denominator, they cancel out, and you get this expression that is given by PT by KT into the bandwidth. And now in place of this, you can also put these expressions of that is the EIRP PT into GT divided by K into B by, and this lambda by 4 pi r whole square GR by TS. Okay, that means if you simply put the value of these the received power in that expression, the received power is your carrier and the noise is simply given by kT into B. If you simply put that, you will ultimately arrive at this relation, that is this PT into GT is the EIRP divided by KB. This is coming from the noise power contribution, and TS is nothing but this T, and lambda by 4 pi r square that was there in that expression for PR. Okay. So this G by T over here, this is actually, the kind of parameter which tells us about the performance of a particular earth station. It is a kind of figure of merit of an earth station. That means in this earlier expression, we were trying to understand that in Freeze transmission equation, this PT was not within the control of the user, the receiver, so also the GT, because these are designed and controlled by the corresponding organization which has launched that satellite, designed that satellite. Lambda, that is the frequency or wavelength at which the transmission takes place, that is also fixed, and the distance of that satellite from the receiver, that is also fixed. So what we had seen is that when we talk about the received power, only the gain of the receiving antenna, that is what is at the disposal of the user by making the value of this gain as large as possible. There they can actually increase the value of the received power. So here also, from the carrier to noise ratio, what we can see is that this factor GR by TS, this is the kind of proxy indicator for the carrier to noise ratio. Proxy indicator, that means it is not exactly the carrier to noise ratio, but because the other terms like this EIRP, the Boltzmann's constant, the bandwidth of the receiver, these are more or less constant, because one cannot go on increasing the bandwidth of the receiver. Increasing the bandwidth, that has got a negative effect, as you can see, the carrier to noise ratio, that will fall. And also this lambda and R, they are also not controlled, they cannot be controlled by the user. So basically it is only this ratio GR by TS, that is the gain of the receiving antenna divided by the noise temperature of the earth station. That is what would be controlled. That means we should try to make the gain of the receiving antenna as large as possible and the noise temperature as small as possible. Okay, that way only the carrier to noise ratio will increase. Okay, so towards that end, for a standard A earth station, that means earth stations are classified according to the value of the GR by TS which they possess, and a standard A earth station is like one which uses a G by T ratio of 40.7 dB per Kelvin. Okay, that means GR is in dB and TS is in Kelvin. So that is why the unit is dB per Kelvin. And there, while specifying this G by T ratio for the earth station, the corresponding frequency and the elevation. This elevation is also important, because you see, as we are trying to track a signal from a satellite, when we go to very low values of elevation angle, that means the ray path is almost like grazing the surface of the earth, or passing a long distance through the lower part of the atmosphere, the possibility of additional noise being introduced into that signal, that increases. That means higher is the elevation angle of any particular satellite link or radio link, less will be the amount of noise which will be coupled onto that signal. So that is why it becomes important to specify what is the elevation of that particular radio link in terms of its value. And usually, although this value is with respect to 5-degree elevation, but I can tell you that it's not advisable to go for satellite links which are at low elevation angles of like 5 degree or so. Typically, for communication satellites, like some of the problems which we had done in some of the earlier classes, that means where we have calculated the elevation angle of some geostationary communication satellites like FleetSatcom or Inmarsat from Calcutta. So there we had seen that the elevation angles of these satellites from Calcutta were quite high, like more than 50 degree. Okay. So that is why the quality of an earth station that is specified with respect to usually some of the worst case figures. Okay. That means if it goes below this, then it is not acceptable. So that is why if it is more than that, no problem. That means as you go to higher and higher elevation angles, the value of this G by T that will also improve because the noise contribution coming, additional noise component coming because of the ray path being at a lower elevation angle and hence coupling more noise from the lower atmosphere, that gets reduced. So once that noise contribution gets reduced, your G by T ratio increases because the carrier to noise ratio also increases. So let us now try to work out this simple problem and of G by T, calculation of G by T ratio. So will you please write down this problem?
Yes, sir. Yes, sir.
An earth station antenna has a diameter of 30 meter and overall efficiency of 70%. An earth station antenna has a diameter of 30 meter, has an overall efficiency of 70%, and is used to receive a signal at 4150 megahertz. At this frequency, the system noise temperature is 80 Kelvin, 80 K, when the antenna points at the satellite having a subsatellite point of 75 degree east. Calculate the elevation of the satellite. That is the first part. Calculate the elevation of the satellite. from Calcutta. The second question is, what is the Earth station G by T ratio? What is the Earth station G by T ratio under these conditions? So tell me, calculate and tell me the values. Yes, so what is the elevation?
So G by T ratio is 41.75 dB per Kelvin.
No, first tell me what is the elevation. Elevation of the satellite. Monisha De,
Yes, sir, I'm calculating.
you are calculating?
Yes, sir.
So what is the value of elevation that you have got?
Sir, 1 second, sir, I'm taking.
Okay. Aniruddha Mondol? Are you there? Aniruddha Mondol? Are you calculating? What's the value of elevation?
Sir,
Yes.
sir, I got a value of around 59 degrees.
Elevation.
59.4. Yes, sir.
Okay, let the others also confirm. Ognisha, are you doing?
Yes, I'm calculating.
Okay.
Sir, 59.3 degree.
59.3. What's your name?
Srija Chakraborty.
Okay. Okay, so moving ahead, I hope you will be able to solve that problem. It's nothing difficult, only putting the values, and the value of the G/P ratio will be around that 40 to 45, that range, dB per Kelvin. So now, since we are now familiar with the fact that design and launch of a geostationary satellite is an extremely expensive proposition, so that means once we launch that kind of a communication satellite, we should try to maximize, I should not say maximize, we should try to optimize its utilization as much as possible. That means one of the things will be, of course, we would like to have as many users accessing that particular transponder or a number of transponders on board the satellite. But at the same time, there should be some, kind of control on the authentication of the users who are accessing that particular transponder, because satellites or any kind of space asset is a sensitive infrastructure. It could be used for good purpose, it could be used for harmful purposes also. So that's why we should try to optimize the accessibility of the satellite links. And for that purpose, there are different kinds of techniques. One of the techniques that we have already learned about is the frequency reuse. But other than frequency reuse technique, there are like multiple access techniques which are also used. And when we talk about multiple access, basically the uh, problem that we have to keep in mind is that there will be a kind of continuously changing pattern of users accessing that site. It is not that it's a fixed user and a fixed receiver. It's not that kind of a dedicated communication link. That kind of service also exists for satellites, but that is like you know usually used for defense purposes. That is, you have a dedicated transmitter and a dedicated receiver on the surface of the earth, and it is not a broadcast signal that they handle. So when we talk about accessing the transponders on board a satellite by different users, so one thing that we should keep in mind is that from common sense we can understand that we could either allocate a fixed proportion of the resource. What is the resource in this case? The resource could be, for example, the total time over which one could access that particular satellite. It could be the different frequencies or the bandwidth of that transponder. So these are the two main kind of resources which are available, and we could either allocate a fixed proportion of these resources to each particular Earth station well in advance, or the modern concept is that this resource is allocated as and when needed in tune with dynamic traffic condition. Okay, by traffic we mean the volume of information or data that is flowing. So that could be like demand access. So either you can have fixed access or pre-assigned access, where the proportion of resource which is allocated is fixed in advance, or you can have demand access or demand assignment. So one of the both the systems have their pros and cons. Now, fixed access was the traditional way in which multiple access techniques they were kind of configured. The systems were configured, but there, after say for example, let us take the example of India, for example. So here, what we observe is that normally post 1990, when all this IT boom and other things happened, and post that period, after that period, for example, between India and US, we could find that larger volume of traffic is there during the Indian night time, because that is the daytime in the US, the office hours in the US. And with Europe, of course, it's a little bit less, the time difference, like it could be about 5 to 6 hours of difference. So that means that during the daytime, or maybe some portion of the day, the volume of traffic will be less flowing from India to some of the Western countries compared to other periods of time. But if we have a fixed access or a pre-assigned access, then in that case, because the proportion of the time or the number of carrier frequencies or bandwidth which has been allocated to a particular Earth station is fixed in advance, so there is no way that we could dynamically assign them to other Earth stations who may be needing that. Like somebody doing business with the Middle East or maybe with the Southeast of Asia. They may be needing more of that during the daytime. But because we have a Indian daytime, but because we have made a fixed proportion available to some other Earth station, so that is kind of a wastage of resources when it is not so much used. So that concept or that problem actually gave rise to this concept of demand access or demand assignment. And this demand access or demand assignment also comes into the picture very, it plays a very important role. Like, for example, there is some kind of a natural disaster, or there is some major, kind of air crash or some other thing which has happened. So that region where this natural disaster or calamity has happened, they may be needing more amount of the bandwidth or time in those times. So therein also for search and rescue operation, this dynamic access or demand access, that becomes important at that time. And the classical multiple access techniques are, like, you may be all familiar with them. They are also used in other branches of communication, not only in satellite communication. So they are like the frequency division multiple access or FDMA, the time division multiple access or TDMA, and the code division multiple access or CDMA. Although these are classical techniques, and nowadays, modern day multiple access is more, it has evolved in a more advanced way, and you can have hybrid combination of all these different multiple access techniques. Like there may be a kind of, combination of FDMA and TDMA, or some other combinations, which are more like a hybrid mode of access. So these will become clear as we go further into this topic. But let me stop here for today, and we will continue in the next class. Now, do you have any information about your mid-sem examinations?
No, sir.
Your coordinator is Pulak Mondol, right?
Yes, sir.
Okay. So maybe you can ask him.
Okay, sir.
What about the other courses? I mean, they are going on.
Yes, sir.
Okay. 301. 302. 303.
Present, sir.
305.
Present, sir.
306.
Present, sir.
308.
Present, sir.
309.
Present, sir.
311.
Present, sir.
313.
Present, sir.
314.
Present, sir.
315. 316. 317. 318. 319. 320.
Present, sir.
321.
Present, sir.
322. 323. 401.
Present, sir.
402.
Yes, sir.
405.
Yes, sir.
407. 408, 411,
Present, sir.
414, 420,
Present, sir.
421,
Present, sir.
422,
Present, sir.
423, 424, 430,
Yes, sir.
431,
Yes, sir.
432, 433,
Yes, sir.
435, 436,
Present, sir.
436, present.
Yes, sir.
437,
Present, sir.
438, 439,
Yes, sir.
440,
Yes, sir.
441, 442,
Yes, sir.
Shayan Datta,
Present, sir.
Ravi Kumar Thakur.
Present, sir.
Okay. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.